All right, we're gonna do two sections today. We're starting with 3.5, which is on local linear approximation and differentials. So we're gonna let y equal f of x. We often do this. And we're gonna say it's differentiable at x. And suppose that dx that's what we call a differential. Uh, denotes an arbitrary increment of x. The corresponding differential for y we call dy is defined by dy equals f prime of x dx. This would be an easier way to remember this. F prime of x is slope, right? Slope of the tangent line, which is a change in y over a change in x. Or like a delta y over a delta x. So without putting the tangent stuff in there, I've got delta y over delta x. If I cleared fractions, because these are values here. Multiply both sides by it, I get delta y equals f prime of x delta x. I cleared a fraction. And as I go through this later on this lecture, you're gonna see how delta y corresponds to dy and delta x corresponds to dx. They're very close to each other. One's an approximation of the other. That might get a little bit easier to memorize. It comes from tangent line, and as long as you know what the slope of a tangent line means. And one application is error propagation. Propagation. Not a word you say very often. In reality, when we measure shit. The accuracy of our results. Is limited by the tools we use. Like when you look at a ruler. The little fucking increments go down, you get down to half inch, just quarter inch, eighth inch, 16 inch. Some rulers might show a 32nd of an inch. But after that, you're like, I'm between two of them, I'm gonna pick one. You know what I mean? So like you're losing some accuracy there. On a scale, the scale doesn't show 10 decimal places. You go weigh yourself, most scales don't even show 1 decimal place, but some do. But you could be more accurate to another decimal place. When if you drive and you're looking at your odometer, a lot of odometers don't show decimal places either, they just show the mileage. Some will show to 1 decimal place, but let's face it, a mile is over 5,000 feet. We could break that up into smaller increments, so there's some error there. And the error ends up being. Our error is. Dx. And we end up using our measurements. To calculate something else. Maybe not when you're stepping on the scale, but like. In the sciences and engineering, when you're measuring stuff, it's often because you need to do something else with it. And so. The error in measurement propagates or transmits. Is carried over to. The results we want. Giving us a dy. Does that make sense? Like how accurate can our answer be if our input wasn't right the first time? This is why you learn about significant figure, significant digits and stuff, because you only want accuracy to what you have. Calculator will fucking show you as many decimal places as possible, but. You weren't accurate to that level in the first place, can't be accurate to that level afterwards. Chance to finish writing that, except Brianne, Effer. Showing away, yeah, all you're gonna see is a big explanation of why we're doing it. We haven't really done anything yet. Let's look at an example. And this example is going to delight Jacob. Because he messaged me about questions about the volume of the sphere. And I said, Google that shit, bro. Suppose you wanted to soak someone with a water balloon. Suppose you were in a water balloon fight. And you're a scientist, you're interested. In exactly how much water you're hitting them with. That balloon holds. So you measure the spherical radius of the balloon. We're going to assume that you're holding it like downwards so that the balloon kind of does fill up like a sphere. Oftentimes when you blow air into it, it works just fine, but water's heavy, so it'll make it sag when you're filling it. But if you point the hose downward, it doesn't do that, it'll fill like a sphere. But you are measuring the radius of the balloon and. You find it to be 3 inches. With a possible error of plus or minus 0.1 inches. What is the corresponding error in the volume of the balloon? So we're trying to make a connection between the radius of the sphere and its volume. Remember what it was, Jacob?
Radius of the sphere?
Well, no, the volume of the sphere.
Oh, I have both of them, but I don't know which one's right. Is it the,
There's only one of them that's right. Which ones do you have?
there's 4/3 times pi times the radius cubed?
That's the volume of the sphere. I'm betting the other one you had was the surface area.
I think it was the one that we solved for in class. That was the other one that I had in my head and was asking you about, so.
Yes. That is the volume of the sphere. So if you want to see generate differentials, it looks like you're doing this, but. Not really. Let's take the derivative. With respect to R. So since the volume of the sphere is a function of R. This will have, it looks like implicit differentiation, but it isn't because it's all on one side. We have dV dr equals. If I bring the 3 down, it's gonna, well, shit, I'll just show it. We've got 4π/3 and then the r cubed becomes 3r squared. And if we clean that up, that is 4πr squared. So right now, this looks like dV dr equals 4πr squared. And the next step. This looks like clearing fractions. And works that way. But it's not really what happens here. Thank you, excuse me. It's just an easier way to remember it. Multiply both sides by dr and we get dV equals 4πr squared dr. I need to get work on making my r's look less like b's. Especially if I'm working with the volume and the radius. They look like the same fucking letter. So this was our differential, our error. And we had a radius. Add or have. We can calculate dV. R was 3 inches. We're squaring that, and dr is plus or minus 0.1 inches. So this ends up, this part's 9 inches squared, we're multiplying it by 4 pi. Then we're shifting the decimal by 1. This ends up looking like plus or minus 3.6 pi inches cubed. Which is approximately plus or minus 11.3 cubic inches. Is that a lot? Is that a big error? It's kind of hard to tell because we don't really have what the volume of the balloon was. Why don't we figure out real quick what the volume of the balloon was? What's the volume ignoring the error? Well, we're gonna come back up here to this equation. The volume is 4/3 times pi r cubed. Which is 4/3 times pi times 3 inches cubed. And we're gonna get 36 pi cubic inches. And 13.1. So it looks like maybe 10%. Let's figure out what it is. To figure out the percentage error here. We're gonna do dV over V. So 11.3, I'll just round that to 113. Over 113 is 0.1 or 10%. Doing that in my head. That seems right though. Yeah, 10%. Seems like a lot of error. This is called the relative error. When we calculate the percentage error, this is called the relative error. Well, maybe the 0.1 is more of the relative error. And when we write it as a percentage, we'll call it the percentage error. Now, since there was some error in our balloon, we don't know that this was the exact volume, the 113. We said there was some error in measurement, but. This is what happens when we're working with relative error a lot. We'll have the quantity Q. And some error in measurement DQ. So as I was saying, the relative error is. DQ over Q. And this is assuming Q is an exact value. But it is. We never have the exact Q. So we approximated. With our measurements. Just as we did here. I didn't have the exact volume of the water. But I approximated using the 3 inches that I had. Second process that, we're gonna do another thing with it. I got another example for you. Actually, before I do, I'm gonna pause this video. Just because it doesn't need to be in the. Okay, so our next example. You are in charge of firing cannon at an enemy outpost. And fuck outpost, enemy's castle, there we go. Take this back to like good old times. I don't know about how good they were. And conveniently, you know the muzzle speed of cannon. You know the cannon fires at 450 feet per second. Fires a ball at a speed of 450 feet per second. Of course, it's trapped by gravity. So like a little picture of your cannon. And it's shooting at an enemy castle. And so it's making some angle theta here with the ground. And you gotta set the right angle because if you aim it too high, the cannonball falls short. If you aim it too low, it may not even make it or it's gonna go over. So that angle matters. You set an angle at 30 degrees. With a possible error of 1 degree. What is the relative error in the cannon shot? And this is assuming you know a little bit about physics, and if you don't, the flight of a projectile follows the following equation. R equals B naught squared sine of 2 theta over G. B naught is initial velocity. And G is a gravitational constant. That is the most awkward spelling of the word constant with capital letters just randomly inserted in there. You're welcome. This is your professional teacher here.
You know what bothers me more than that is how the word enemy is spelled. I feel like there's supposed to be a E in between M and Y.
It's not, that's.
I know that's the
correct.
real way you spell it, but in my head, I feel like it just makes more sense to put a third one in.
And if you don't know the gravitational constant on Earth. What's the gravitational constant for Earth?
Is it 9.8 meters per second square?
That's one version of it. So one version of G, and usually we can take it down. If we go to 1 decimal place, it's 9.8 meters per second. Oftentimes you'll do 9.81 meters per second. Or if you go 3 decimal places, 9.807 meters per second. But my cannon's firing in feet per second, so we don't want that, the metric system. So let's find one in terms of. In feet per second. $32.17 feet per second squared. And these are per second squared too. In fact, I even have it written down to more decimal places in my notes, 17405. If you want to get down deep. And so how does that match up with our picture? Data is obviously there. This distance here is R. Or shot range. R is for range. So, what do you guys want to calculate first, R or DR? We need both if we're gonna do relative error.
Suggest is normally easier to find first. Depending on the situation or.
No, they're both separate paths. Let's do DR first, because if you do R first, you might be inclined to try to start from that value and it's a constant at that point, if you take the derivative, you're gonna get 0, and that doesn't make any sense. So maybe to avoid like understanding errors, let's start with dr. So we wanna take the derivative of this with respect to theta. Dr d theta. We're gonna hit it with that. I wrote that all awkward. Cause that's how I roll. So dr d theta, and I'm gonna move the d theta to the other side. V naught squared is just, it's a constant squared, that's not changing. The sign is gonna go, and neither is the g, those are constants. All that's being really hit with this is sine of 2 theta. Sine of 2 theta is gonna be cosine 2 theta. Then don't forget the chain rule, we gotta go on the inside, times 2. And then a d theta. So 2 v naught squared g cosine 2 theta. D theta. So if we do that, I got 2 times v naught was our initial speed, that 450 feet per second. We're gonna square that. G is on bottom, 32.17. Feel like going to the 4 is better, because rounding off like at 17 is like definitely missing half. Then we got cosine of 2 theta, which is cosine of 2 times 30 degrees. And then we want d theta, but we don't, d theta is a degree. We don't want degrees in our answer. So d theta is 1 degree, but we don't want degrees in the answer. We want to switch this to radians, because radians don't have any units. So let's hit this with pi over 180. And that conveniently becomes our d theta. And that's a plus or minus. Since it says with a possible error and it doesn't indicate which way, plus or minus pi over 180. What's cosine of 60 degrees? What?
Square root of 3/2.
Nope.
Square root of 2/2.
Nope. It's 1/2. You're running out of options. It's not square root of 3, it's not square root of 2, it's square root of 1/2. Alright, so that ends up being 1/2, this is 1/2. We multiply this all out. I'm getting plus or minus 109.85. And that's gotta be in feet. Alright, we need R. R is just plugging into the initial formula though. We got 450 squared. Sine of 2 times 30 or sine of 60 degrees. Over 32.174. And that's about 5,450.67 feet. Other people are doing it on a calculator. If you get something different, let me know. If possible, I made an error. As great as I am, even I make mistakes.
Perfect jokes.
We all have our faults. Mine's in California. I love that line. Does anyone know what that's from? We all have our faults. Mine's in California. Probably a little bit past your time. It's from Superman the movie. Superman 1, Lex Luthor, played by Gene Hackman. It's a phenomenal, this is with Christopher Reeve, Superman, it's an old one.
That makes sense.
Gene Hackman is he's Lex Luthor and he's decided. He loves real estate, he's loved real estate in all Lex Luthor versions love real estate. Well, he's decided that he's gonna buy up most of Central California where land is cheap, where we live. And then fire a nuke at the San Andreas fault line and sink all the expensive coastline into the ocean. And thus making the Central Valley the new coastline, and all the land he bought cheap is now the new west coast of the US. And it skyrockets in price. And that's where he says we all have our faults, mine's in California. It's making reference to the San Andreas fault he's about to nuke. Well, I don't think he nukes it, but hits it with a missile, enough to enough of it, you don't want the radioactive, fallout over your real estate, but.
Seems like
That's a good movie, you guys are missing some good shit.
That sounds good.
it's psychopathic. I mean, smart, but
Lex Luthor is a psychopath. Alright. I got more stories about Lex. Let's see, one more. And another application of differentials. Approximating a tangent line. And this stems from the tangent line approximates the value of x of x, f of x. In a small region around the x you're calculating. Or using. Let's look at that a little bit pictorially. Let's say this is my f of x. And I do my tangent line from here. So I got some point x1. My tangent line does this. Now, and it keeps going. So we can see long ways away, it doesn't really look like it, like. Over here, this value of y is nowhere near this value of y. Right? But close to it, they're pretty close to each other. So we could go over a small distance delta x. So this would be like x1 plus delta x. And showing that here, we're doing that and going up to there. So that's like a delta x. And this is our delta y. But this is where the tangent line's approximating it. And this distance right here is the dy. So the dy is pretty close to the actual difference. We'll put the formula up in a second. In this case, dy is greater than delta y. But I can do the same thing over here with a different point. Make another tangent line. We'll call this x2. And go over, I'm gonna make the difference delta x a little bit bigger, just to make it easier to see. That's delta x and that's delta y. But where it hits the tangent line. That distance is dy. So in this case, delta y is greater than dy. But in either case. They're about the same value. And the equation we're gonna use to do this is f of x plus delta x. Is approximately equal to f of x plus f prime of x delta x. This might look unfamiliar to you, but it is actually very familiar to you. Solve this for f prime of x. To find something familiar. That would require subtracting f of x from both sides. And then dividing by delta x. You might recognize it as f of x plus h minus f of x over h. So it stems from that. And before we use it in an example, I'm gonna like help make it a little bit clearer, I hope. This is a y value. This is a y value. Just a slight distance, small distance away. And like the whole f prime of x times delta x, you're like, what the fuck? But f prime of x is delta y over delta x, and we're multiplying it by delta x. And those cancel. So this is like the y value at y2 is the same thing, or approximately equal to y1 plus some delta y. That's really what's going on here. How is this useful? Like, why would you do this? You don't want to grab a calculator. And you got some weird shit going on, and you know values that for particularly close values. Let's take a look at an example before we hop to a break. We're gonna approximate cosine of 62 degrees. So let's say like f of x is cosine theta. Or cosine x. What's f prime? Negative sine x. Anthony's over there whispering it all the time. He's usually right, he always whispers it, so I have to strain to hear him. We're looking at this formula right here. We're trying to find f of 62 degrees, which is 60 plus 2. We're gonna approximate that as f of 60 degrees plus f prime of 60 degrees times delta x. And delta x is the change in x values. 62 degrees minus the 2 degrees that we're shifting by. Let's approximate it with 60 degrees, which we know, well. Yeah, we just had cosine 60 a second ago. What does this translate to in without the s? Cosine of 62 degrees is approximately cosine of 60 degrees. Plus f prime or minus sine of 60 degrees. Times. Wait, I wrote the wrong fucking value there. 62 minus 60 degrees. Delta x is 2 degrees. I'm like. That looked awkward. This is 2 degrees, but we don't want it in degrees. So we're gonna multiply it by pi over 180. This is approximately 1/2 minus the square root of 3 over 2 times pi over 90. And so that, do that, you can get that. The actual cosine of 62 degrees. 0.4694715562. So it's accurate to about 3 decimal places. Ignoring rounding. And now we hit the 3.5, let's take a 10-minute break. 10 minutes, Jacob and Brianna, not back at 20. Cause the next section, you're gonna
We're waiting on you.
love the next section.
Don't say that to you. I don't know if you're sarcastic.
I'm being serious, L'Hopital's rule is the best thing since fucking sliced cheese.
Having a brain.